Hello, and welcome to another lesson for Math 1106, Math for Business Precalculus. My name is John Adamski. Now this is week 10. We're going to be studying inverse functions. This is going to continue our study of functions, which we've been doing for quite some time. We're going to first learn what it means for a function to be one-to-one. We will see that some functions are one-to-one and some functions are not. If a function is one-to-one, then we can use that function to derive from it a new function called f inverse, the inverse function. It will be clear from the definition of the inverse function that if you started with f inverse and took the inverse of that you would get back the original function. So that functions and it's in their inverse come in pairs in this way. And it will be also clear from the definition that those functions, f and f inverse, interact in a very interesting way when they're composed. Not only interesting, but useful way. That they essentially cancel each other out. That when you compose f with f inverse, you get back what you started with. And vice versa, when you compose f inverse with f, you get back the original input. We'll see what that means and how that's used. And we'll wrap things up with a discussion of graphs. If you are looking at the graph of f, how do you determine what the graph of f inverse looks like? There is a very clear relationship between the graphs, actually a pretty relationship that we will see. And yeah, let's get to it. Let's take a look at these two functions f and g on the board. This is a diagram that explains what the output is for various input. I don't want to get bogged down with the algebraic definition of f and g. I don't want to look at their graphs. I just want to distinguish between them, and this is a nice way to highlight the difference between them. So what this is trying to say is that g of 1 is 8, g of 2 is also 8, g of 3 is 9. Okay, fine. That's a perfectly fine function. I know what the output is based on the input. Down here we have f. This says that f of 1 is 8, f of 2 is 9, f of 3 is 7. Another perfectly fine function. But you may notice that there is something different about them. In g, you have two arrows pointing at the same output. That is to say that g of 1 and g of 2 are both 8. And that is not the case for f. None of the arrows point at the same output for different inputs for f. Every unique input produces its own unique output. That is a distinction between f and g, and we use the word one-to-one to talk about that difference. So this definition says a function f is one-to-one, and that is also called injective in certain textbooks, but for us we'll be calling it one-to-one. F is one-to-one if different inputs always produce different outputs. In other words, if a is not the same as b, then f of a is not the same as f of b. Okay, so this is the word one-to-one that we can use to distinguish between these. F is one-to-one. Okay, f is one-to-one. If you have different inputs, they always produce different outputs. G is not one-to-one. There are two different inputs that produce the same exact output. Specifically, 1 and 2 are two different inputs that produce the exact same output, which happens to be 8. Okay, so why do I care? Why do I care between these differences? They're both perfectly fine functions, but notice that f, because no two inputs produce the same output, what I can do with f is I can reverse the arrows, and I can define in that way a new function. If I make the arrows point in the opposite direction, okay, that creates a new function. I'll call it f inverse, and I'll say that f inverse of 7 is 3. And the reason is because f of 3 is 7. I'll say that f inverse of 8 is 1, and the reason is that f of 1 is 8. And I'll say that f inverse of 9 is 2, and the reason is that f of 2 is 9. Okay? So by just reversing the arrows, I get a new function. Okay? That doesn't work for g. If you tried, you'd end up with a problem here. What would g inverse of 8 be? Well, since g of 1 is 8, you'd want to say that g inverse of 8 is 1. But since g of 2 is 8, you also want to say that g inverse of 8 is 2. So what is g inverse of 8 equal to? Well, there's no way to answer that. This is not defining a function. Okay? I can't do this trick with g. I can do it with f. I can do this for one-to-one functions. What I'm doing is described here. I'm defining an inverse function. It says, given a one-to-one function, like f, the function f inverse, this is read f inverse, is the function defined by f inverse of y equals x if and only if f of x equals y. So that's what I was saying down here. I can define f inverse from f, because f is 1-to-1, in this way. I know that f inverse of 7 is 3, and that's because f of 3 is 7. I know that f inverse of 8 is 1 because f of 1 is 8, and I know that f inverse of 9 is 2 because f of 2 is 9. I'm just running the function in reverse. That's actually a very good way to remember what is going on here. When we talk about inverse, you should think about running the function in reverse. Okay? The words sound the same, inverse and reverse. You are running the function in reverse. This is what inverse functions are all about, and this is the definition. Okay, so here's an example that should get us comfortable with the definition of an inverse function, and that should also illuminate the cancellation properties that inverse functions satisfy. So let's get started. I've got a function f, and I'm telling you that it's 1-to-1. So it has an inverse function. And I'm giving you some information about f, what some outputs are based on certain inputs. Okay? And I ask, what is f inverse of 76? Well, remember from the definition of f inverse of y is x if and only if f of x is y. One way I like to think about this is that both of these are conveying a relation between x and y. You can start with x and input it into f to get y, or you can start with y, input it into f inverse, and get x. Another kind of relationship that we have inverse relationships like this for is if my dad were to walk into the room, I could say, he is my father, or I am his son. Okay? It depends on who you start with and who you end with. It's describing the same relationship, but in different words. It's the same thing here. F of x is y, f inverse of y is x. He is my father, I am his son. Try and keep that in mind. So what is f inverse of 76? Well, I know that f of 2 is 76, so f inverse of 76 is 2. That's what this says. F inverse of 76 is 2, because f of 2 is 76. And then, as a follow-up question, what is f of f inverse of 76? Well, we already know that f inverse of 76 is 2, so this is saying what's f of 2, and that's 76. Okay, let's try another one. F inverse of 53. Well, the chart makes it clear that f of 4 is 53. So I guess f inverse of 53 is 4. That's correct. F inverse of 53 is 4. And knowing that f inverse of 53 is 4, f of f inverse of 53 is f of 4, which we just said was 53. Okay? Now there's a pattern going on over here. When I input 76 into f inverse and then pass that off to f, I get right back where I started at 76. And when I input 53 into f inverse and pass that off to f, I get back 53. And by the way that inverse functions are defined, maybe that's not surprising. F inverse of 92 would be 1, because f of 1 is 92. And f of f inverse of 92 is 92. Okay, that time I just stated it right away, because I know f inverse of 92 is 1, and f of 1 is 92. Correct? Now f of 3 is 68. What's f inverse of f of 3? Well, that's f inverse of 68. And since f of 3 is 68, I guess f inverse of 68 is 3. Once again, I'm composing f and f inverse and getting right back the original input that I started with. Okay, one last example. F of 5 is what? F of 5 is 49. Okay, so f inverse of f of 5 would be f inverse of 49, which would be 5. Okay, so if we just look at what's going on over here, it seems like you could write down these answers right away. It seems like if you have f inverse inside of f, it seems like they just cancel each other out, and you get right back what you started with. Same thing if you put f inside of f inverse, you get right back what you started with, 3 and 3. That is the cancellation property that inverse functions satisfy. Though there are two. There are two cancellation properties of inverse functions, and this is what they say. Given a one-to-one function f, since it's one-to-one, you can talk about f inverse. Not every function has an inverse function, but one-to-one functions do. And given a one-to-one function, you have f inverse. If you compose them, if you put one of the functions inside of its inverse, you get back exactly what you started with. Okay? F inverse of f of x is x. F of f inverse of x is x. There is something to be careful about here. In the top line, it says f inverse of f of x is x for all x in the domain of f, for all x in the domain of that inner function. And that's what the bottom line says too. F of f inverse of x is equal to x for all x in the domain of f inverse. F inverse is that inner function. That's not something to really worry about, okay? What I really want you to embrace are these cancellation properties right here, okay? However, let's address what this is saying. This part about being careful about domains is preventing me from spewing nonsense, okay? I can't say that f inverse of f of 10 is 10. I can't say that. The reason I can't say that is because I don't know what f of 10 is. Looking at my chart, I don't know what f of 10 is. For all I know, 10 is not in the domain of f. In fact, if this is all I know about f, I have to say that 10 is not in the domain of f. So for that reason, this doesn't make any sense. I don't know what f of 10 is, and so I can't speak about what f inverse of f of 10 is. Similarly, I can't say anything about f of f inverse of 99. Okay? You might want to say that that's 99, right? That's what the cancellation properties are telling me, and that would be a good instinct to have, that these cancel and the answer would be 99. However, I don't actually know what f inverse of 99 is. 99 is not in this column, okay? So I don't know what f inverse of 99 is because I don't know any x for which f of x is equal to 99. So for that reason, I can't make these conclusions. These are not true, and the reason is that these values are not in the domain of the inner function, okay? So be aware of this, but don't let that take away from your instincts that f and f inverse cancel. That is the important thing, and 99% of the time, that's how this works, okay? You just want to be careful that you're not just making cancellations when really the inner functions, when the values are not in the domain of the inner functions. You do want to be aware of that on some level, okay? Okay, let's look at another example. I'm going to continue to use that same function f, and we've, at this point, know very much about f inverse. We've been talking about f inverse. F is one-to-one. It has an inverse function. You know that if I set y equal to f of x, then x is equal to f inverse of y. So this table is not only a table of values for f, but it is also a table of values for f inverse when you read it from right to left. Namely, f inverse of 92 is 1, f inverse of 76 is 2, etc. Okay? Now, what I want to do is use these cancellation properties of f and f inverse to solve some equations. Here I've got f of 2x minus 7 equals 68. Now notice that 68 is in the domain of f inverse. You can take f inverse of 68, right? And since the left-hand side is equal to 68, you can take f inverse of the left-hand side also. What would happen if I did that? What would happen if I took f inverse of both sides? Well, this is what it would look like. You'd have f inverse of f of 2x minus 7 equals f inverse of 68. Okay, and from what we were just talking about in the last example, and what's summarized here in these cancellation properties, is that when you compose f with f inverse, you get back what you started with. Okay, f of f inverse of x is x. F of f inverse of 2x minus 7 is 2x minus 7. That's what this cancellation property is trying to say, that when you compose those two functions, you get back what you started with. And on the right-hand side, I actually know what f inverse of 68 is. It's 3. So this equation boils down now to just 2x minus 7 equals 3. If I add 7 to both sides, I get 2x equals 10. And if I divide both sides by 2, I discover that x equals 5. Okay? Just to check that, 2x minus 7 would be 2 times 5 minus 7. 10 minus 7 is 3. This says that f of 3 is 68, and that is true. F of 3 is 68. So we've checked our answer. Let's try this one. This one has 8x plus 4 inside of f inverse, and it says that that is equal to 1. Okay, now notice that 1 is in the domain of f. So you can take f of 1, and since the left-hand side is equal to 1, you can take f of the left-hand side. That makes sense. What happens if I do that? Well, I'll get f of something equals f of something. F of f inverse of 8x plus 4 is equal to f of 1. And once again, I've composed inverse functions, and they cancel each other out. Okay? So in this case, I have 8x plus 4 equals f of 1, which is 92. Okay? And if I continue on here, I'll subtract 4 from both sides. I find out that 8x is equal to 88. And if I divide both sides by 8, I get that x is equal to 11. You can check this answer. If x is 11, then 8x plus 4 is 92. And this says that f inverse of 92 is 1, and f inverse of 92 is 1. So this also checks. So maybe you, whether you know it or not, you've been doing this for a while now. You've been taking both sides of an equation and inputting them both into functions. You're doing that every time you double both sides, or add 1 to both sides, or take the square root of both sides, or square both sides. You are applying functions to both sides of equations all the time, whether you know it or not. Now we're doing it explicitly, where we're just saying f of the left-hand side equals f of the right-hand side, or f inverse of the left-hand side equals f inverse of the right-hand side. And that's a legal move, as long as the numbers that you're using are in the domains of the functions that you're using. But we were careful to make that check, and everything was fine. Here's another example to really help us understand this important interaction of inverse functions when they're composed, that they satisfy these cancellation equations. Suppose I tell you f of x is 4x minus 8 and g of x is 1/4 x plus 2. Now it turns out that these functions are inverse functions of one another. And I want to show that they are inverse functions of one another by showing that they obey the cancellation equations, which is to say that when you compose these functions, whether you do f of g of x or you do g of f of x, either one is going to return right to the original input. Okay? No matter what x is, f of g of x and g of f of x are x. Okay? That is to say that these functions undo each other. They are inverse functions. They obey these cancellation equations. Okay? Or in other words, g of x is f inverse of x. It's behaving like f inverse. And f of x is g inverse of x, that it is behaving like g inverse. Okay? Let's see. So I have two things to show, actually. I have to show that f of g of x is x. So let's start there. Let's start with f of g of x. Well, that's f of 1/4 x plus 2. Okay, so I have to input an expression into f. What does f do? It takes its input and multiplies it by 4, and then it subtracts 8. That's what f does to its input. If the input happens to be 1/4 x plus 2, then it's going to do that to 1/4 x plus 2. Okay, now I just have to simplify this and cross my fingers and hope that I get x. Well, if I distribute the 4, I see that 4 times 1/4 x is just x, and 4 times 2 is 8. And there's still a minus 8 over here. X plus 8 minus 8 is equal to x. That works. Okay. Let's see, what is g of f of x? G of f of x, well, that's g of something. It's g of 4x minus 8. Okay, so I have to input the expression 4x minus 8 into g. G is this function that takes its input and multiplies it by 1/4 and then adds 2 to that. Okay, so if the input happens to be 4x minus 8, this is what it is. If you distribute the 1/4, 1/4 times 4x is x. 1/4 of negative 8 is negative 2. And we still have to add 2. So this is x minus 2 plus 2. That is x. So this works. Okay? When you compose f and g, they undo each other. You get right back where you started. That is this defining characteristic of inverse functions. That is that is to say that these functions are satisfying the cancellation equations. That makes them inverse functions of one another. Okay? And actually, we maybe could have seen that right from the beginning. If you think about what f does, well, f does two things. It takes its input and multiplies by 4, and then it subtracts 8. Okay? No matter what the input is, this is what it does to the input in that order. Now, what does g do? Well, I'm going to rewrite g because I was trying to hide it. But what g does, you could say that you could rewrite g as x plus 8 divided by 4. That's the same thing as 1/4 x plus 2. Okay? And if in words, what that's doing is that's taking the input, and the first thing it does is it adds 8. And the next thing it does is it divides by 4. Well, let's think about this. If you were to compose them, like we did here, f of g of x, that means g acts first. So first you add 8 and then divide by 4. But then you multiply by 4 and you subtract 8. Well, that just undoes f is undoing everything that g did. It's performing the opposite operations in the opposite order. Pick any number you want. Add 8 to it, and now divide the answer by 4. Now multiply that by 4 and subtract 8. You are right back where you started. That's not magic. That's just inverse functions. And it works the other way, too. If I did f first and g second, then I'm asking you, pick any number, multiply it by 4, now subtract 8. Okay? Now add 8 to that number and divide it by 4. You are right back where you started with the original number. It's not magic, it's inverse functions. Okay? And this confirms that these two functions are in fact inverse of each other. This idea of inverse functions undoing each other is so important to understand. I do want to do one more example that's very similar. Okay? Another analogy you could say is that if f is tying a knot, then f inverse is untying that knot. It is performing the opposite operations in the opposite order. Okay? So anyway, here's a function f and a function g. I want to show that they are inverse functions of each other by showing that they satisfy the cancellation properties, okay, the cancellation equations. So I have two things to show. First, I want to show that f of g of x is x, and then I want to show that g of f of x is x. So let's start with f of g of x. Okay, that's f of, we have x minus 5 divided by 2. Take the cubed root. All right, that has to be input into f. So what does f do? F takes its input and cubes it, and multiplies it by 2, and then adds 5. This is the template for f. Okay, I'm ready to input anything I want into f. I want to input this expression into f. So to copy and paste that down here. X minus 5 divided by 2, take the cubed root. Okay? Now, the rules of exponents say that when you have nested exponents like this, you multiply them together. And 1/3 times 3 gives me 1. So they essentially cancel. Now I've got this fraction times 2. But this fraction has a 2 in its denominator. That 2 and that 2 now cancel. Okay? The order in which I'm doing this kind of matters. So the fact that I handled the exponents first was important because you do exponents before you do multiplication. Now I've got 2 times x minus 5 divided by 2 plus 5. I just want to show the order in which I'm doing this. Now the 2's cancel. Okay? And once the 2's have canceled, this says x minus 5 plus 5. Obviously, the minus 5 and the plus 5 cancel at this point, and you're left with just x. Okay. That's what we were hoping for. Now let's show that it works when the functions are composed in the opposite order. Let's look at g of f of x. Okay, well that's going to be g of 2x cubed plus 5. So I have to input this expression into g. What does g do? Well, g takes its input, subtracts 5 from it, divides that by 2, and the last thing it does is it takes the cubed root of that. Okay? So that's what it does to any input. What does it do to 2x cubed plus 5? Well, let's see. If I put 2x cubed plus 5 into this function, what do I get? Well, the parentheses in here, there's nothing, I can't actually combine those. They're not similar terms. So I can remove those parentheses, and now I have 2x cubed plus 5 minus 5. Well, the plus 5 and the minus 5 clearly cancel. Okay? Now I've got x cubed being multiplied by 2 and divided by 2. Those also cancel. Okay? Maybe it's a good idea to clean this up at this point. I have x cubed inside parentheses. It's actually the only thing that's left inside parentheses, and it's being raised to the power 1/3. We've already said that when you have nested exponents like this, you multiply them. These exponents multiply to be 1, so they cancel, and you're left with just x. It works. These two functions, f and g, are inverse functions of one another. And once again, there is a way of looking at this where you can tell at a glance that they are inverse functions. If we look at what f does to its input, what does it do? And be careful about the order of operations. Beginning with x, what does f do to x? Well, it cubes it. That's the first thing it does. You do exponents first. We're going to cube it. Then we're going to multiply the result of that by 2, so we're going to double it. And the last thing we're going to do is we're going to add 5. Okay? That's what f does. What does g do? Well, the first thing that you do to x inside of g is you subtract 5. The second thing you do, after you subtract 5 from x, you divide it by 2, or you cut it in half. And the last thing you do is you take the cubed root of the result. If we look at this, we can see that these functions are doing the opposite operations in the opposite order. F cubes, doubles, and adds 5, while g subtracts 5, cuts in half, and then takes the cubed root. G undoes f, and similarly, f undoes g. G subtracts 5, cuts it in half, and takes the cubed root. The first thing g does is cube it, canceling the cubed root. The second thing it does is double it, canceling the half. And the last thing f does is add 5, which cancels the subtraction of 5. So it's not surprising that these functions undo each other, and that when you compose them, you get back exactly what you started with. Think of a number, cube it, double it, add 5. Now subtract 5, cut it in half, and take the cubed root. You're right back where you started. It's not magic, it's inverse functions. It's running functions in reverse. Lastly, let's bring graphs into this discussion of inverse functions. Okay? As a review, what's the role of graphs in studying functions? Well, if I know that f of a equals b, then that tells me that ab is a point on the graph y equals f of x. Okay? This is telling me that the y coordinate is f of the x coordinate. So if f of a is b, then f of this x coordinate is that y coordinate. It satisfies this equation. It is on the graph. Okay? Now, if f is a one-to-one, so we understand the connection here. If f is a one-to-one function, then there is an inverse function. And knowing that f of a equals b, another way to say that, remember, he is my father, I am his son. The other way to say that f of a is b is to say that f inverse of b is a. All right? Well, what does that mean in terms of graphs? F inverse, the function f inverse, has a graph. And what do we know now? Well, we know that the point b comma a, would be a point on the graph of f inverse. Okay? Y equals f inverse of x. A equals f inverse of b. The y coordinate equals f inverse of the x coordinate. That's what puts this point on the graph of f inverse. So we understand how f of a equals b implies that f inverse of b equals a. And this statement means that b comma a is on the graph of f inverse. So all four of these are actually just saying the same exact thing. And what I want to be able to do is to go straight from something I know about the graph of f to something I know about the graph of f inverse. All right? All four of these are saying the same thing. And so if I'm looking at the graph of f, I can immediately say something about the graph of f inverse. Namely, point by point, every point on the graph of f determines a point on the graph of f inverse, and you get it by simply switching the x and y components. Okay? When I switch x and y, I get a point on the inverse function. And vice versa. If I switch these x and y, I get a point on that function. Okay? They're inverse functions of each other. So what does that look like? Well, I've got some points here. Okay, and let's say that these are points on the graph of f. So I didn't draw this before, but let's say this is the graph of f. So in white, I'm showing you the graph y equals f of x, and I've highlighted a couple points on that graph. Well, one point at a time, you can tell me points that are on the graph of f inverse. All you have to do is switch their coordinates. Okay? So if I switch the coordinates of 4, 1, I get 4, negative 1. If I switch them, I get negative 1, 4. That would be negative 1, actually, I'm sorry. This is the point. Negative 4, negative 1. If I switch the x and y components, I get negative 1, negative 4. That would be down here. Negative 1, negative 4. Okay? So this point goes to this point. This point, negative 2, 1. Where does that go? This is a point on the graph of f. What's the corresponding point on the graph of f inverse? Well, it's going to be 1, negative 2. 1, negative 2. That would be down here. Okay? Here's negative 1, 3. Switch its coordinates, and you get 3, negative 1. Okay? 1, 4, you switch its components, you get 4, 1. And the last point, 4, 5, if you switch its x and y values, you get 5, 4. 5, 4 would be here. Okay? And if you were to reflect all of the points in the middle on the lines connecting these points, you would get the lines connecting these points. So to reflect the entire graph, this is the graph of f inverse that I'm showing down here. Here's y equals f inverse of x. And there is a nice geometric pattern to what I just did. What I was doing was reflecting the graph of f across this diagonal line. Okay, this diagonal line has the equation y equals x. That's 0, 0, 1, 1, 2, 2, 3, 3. The equation of this diagonal line is y equals x. It's a straight line with slope 1. And all I was doing was reflecting all of these points across this diagonal line. That's what I was doing. And I was doing it one point at a time, but the entire graph of f inverse is obtained by taking the graph of f and reflecting the entire graph across this line. And that's what this theorem over here says. It says that the graph of f inverse is obtained by reflecting the graph of f across this diagonal line, y equals x. So we're just reflecting this graph across this line. We are rotating it across this line. And that makes sense because when you are switching the roles of x and y, which is to say you're just switching the roles of inputs and outputs, you are running the function in reverse, right? As an inverse function, you're running the function in reverse. So outputs become inputs, y becomes x, and when you switch, say, the positive x-axis with the positive y-axis, when you switch them, that is a rotation. That is a rotation across this diagonal line. Okay? And the pretty picture that results is that the graphs are symmetric across that main diagonal line. Just for some extra practice, Let's do that again. Let's say that f is a one-to-one function and I'm looking at its graph. Okay? Can you sketch the graph of f inverse? I say f is one-to-one so that it makes sense to talk about f inverse. What does its graph look like? Well, we can go 1 point at a time. Maybe starting here, I'll take 0, 1. I'll reflect it across this main diagonal. It'll go to 1, 0. I'll take 1, 2, send it to 2, 1. 2, 4 becomes 4, 2. 1, 2, 3, 4, 2 would be here. Okay? And this point here, negative 1, 1/2. I've switched the x and y coordinates. I get 1/2, negative 1. Negative 2, 1/4. I switch the x and y. I get 1/4, negative 2. Okay? And of course, I can now just kind of connect the dots. But notice that this yellow line, this yellow graph, is getting closer and closer to the x-axis as I go to the left. It's becoming more and more horizontal. And remember that what we're doing here is we're just reflecting this graph across this diagonal line y equals x. I didn't draw it until now because I wanted to go just coordinate-wise, reflecting these points, switching their x and y coordinates and just doing it that way. But I was reflecting all of these points across this line. That's what I was doing. Okay? And when you reflect a horizontal line across this diagonal line, it becomes a vertical line. Okay? So that can also help me to draw this. When this is getting closer and closer to the x-axis, its reflection will be getting closer and closer to the y-axis. And the reflection of this graph is going to have this sort of shape. Okay, we can see that it is symmetric across this diagonal line. The equation of that diagonal line is y equals x. We reflected each of these points across that diagonal line. We reflected then the entire graph across the diagonal line. This is our sketch of y equals f inverse of x.